Hi everybody, Dr. A here, and in this video we are going to be providing some background information and some governing equations regarding axial deformation. So let's go ahead and get started. If you recall from a mechanics of materials or structural analysis perspective, an axially loaded member is one that supports forces directed along the member's longitudinal axis. All right, so for example, if you have some type of member, a bar or a rod that has some length L, it would be considered axially loaded if it has forces F acting along its longitudinal axis, okay? So the forces are directed along the length of the member. That would be axially loaded, okay? And so this particular diagram is showing an axially loaded member in tension. We could also have an axially loaded member in compression, okay? So that would be the forces are tending to compress the member, but they're still directed along the longitudinal axis. So this is a compressive sense. This is a tensile sense, okay? Now, whenever a member is axially loaded, it will tend to deform, okay? And so we can start to explore this idea of elastic deformation of axially loaded members. So the governing equation for elastic deformation of axially loaded members due to axial loads is given as the following. We have delta, which is our deformation. This is our axial deformation, and in general that can be written as the integral from 0 to L, P as a function of x over A as a function of x, E as a function of x, dx, okay? Where P as a function of x is the internal force as a function of location x, and then of course A as a function of x is the cross-section area, again as a function of x, and then E as a function of x is modulus of elasticity, or of course we sometimes call it Young's modulus as a function of x along the member length. And then of course L is the member length, okay? And so the thing we have to keep in mind here is when we're applying this formula, P as a function of x is not the applied load, really. It's the internal force in that member due to applied loading, okay? Now, whenever all of these values are constants, you know, this is the general integral. Whenever each of these values is a constant and not you know, a variable function, then this formula simplifies. So for all values constant, we'll have delta equals PL over AE. Okay, so this is a greatly simplified version of this integral formula. Okay, and of course the L comes out because think about it, when you integrate from 0 to L, the dx is your differential length, and so when you have everything constant, then your dx just becomes the total length. Okay, now what happens if you have a segmented bar? Okay, so for a segmented bar, for example, let's say you've got, you know, a bar that has some different segments with different properties. I'm just drawing, you know, something like this, and this is maybe bar number 1, or segment number 1, segment number 2, segment number 3, and of course, you know, you could have an E1 and an A1, you can have an E2 and an A2, and you can have an E3 and an A3, and of course, you know, you can have a length 1, length 2, length 3, so on and so forth. If you have a segmented bar and each of those segments is supporting constant values for each segment, then we can write the following version of the formula. We can have delta equals the summation of PL over AE sub I, where I goes from 1 to n, where n equals the number of segments. And again, number of segments, each with constant values of P sub I, L sub I, A sub I, and E sub I. Okay, so again, this is the summation version of that formula. Again, when you have segments, but on each segment you have constant values. Okay, so that's it basically in a nutshell. And the way you can kind of think about this is in terms of our sign convention. Positive values are tensile and negative values are compressive. Okay, so this is our quick overview of axially loaded member deformation subject to forces, subject to applied loads. In a separate video, I'm going to talk about axially loaded member deformation due to thermal effects. So that's going to be in another video you should look out for. All right, thanks for watching.